right. We're going to answer it. So, here we go. Lecture 2-2, linear algebraic eigenproblem. So, you guys have encountered eigenvalues and eigenvectors in your differential equations class. I checked. So, and
took it over the weekend.
those of you who are in linear algebra, I know you're not there yet, but you'll have 2 passes at it, which will help you in the second pass. First pass, you're still screwed. But it's actually a pretty simple problem. So the linear algebraic eigenproblem is for an n by n real matrix A, an n by 1 complex matrix or complex vector M, and lambda, a complex number. M is defined as an eigenvector if if and only if it is non-zero, and if you multiply M, left multiply by the matrix A, and if you scale M by a factor lambda, then they're equal to each other for some specific lambda. And if there is such a lambda that gives you that equality, then it's called an eigenvalue. So that's really it. I mean, I should just drop the mic and we should go. And that's the end of the lecture. But I'll expand on that a little bit. That's the whole thing, though. That's the eigenproblem. So we'll talk a little bit about how to solve the eigenproblem. So that is M is an eigenvector of A if its linear transformation by A is equivalent to its scaling. So if you take M and you hit it with a matrix A, that's equivalent to just scaling M by some factor, lambda. So that's what makes M an eigenvector, if this equality is true, and that is what makes lambda an eigenvalue corresponding to that eigenvector. Since a matrix can have several eigenvectors and corresponding eigenvalues, we typically index them with a subscript. For example, M sub I pairs with lambda sub I. So M1 and lambda 1 go together, M2 and lambda 2 go together, etc. Okay, so solving for eigenvalues. So solving for eigenvalues and eigenvectors is what the rest of this lecture is going to be. There's like a little bit of, I don't know what it is. Something's in the air around eigenvalues and eigenvectors. People think they're scary. Not scary. They're like pretty straightforward. So especially because I'm not making you guys deal with a special case of generalized eigenvectors. It's a little tougher. But so solving for eigenvalues. Equation 211, so this one, can be arranged as follows. So 212, this is actually the form of this equation that we'll typically use because it's more convenient algebraically. But all we did was subtract AM from both sides and then factor out the M. So that's what we did. We also switched the left and right hand sides. For those of you who are keeping score at home, that's what happened. For a non-trivial solution for M, so I'm just stating this as a fact. You guys, in linear algebra, you probably actually motivate this. So I'm just stating it, and then in linear algebra, they'll probably either prove it or explain why this is true. But for a non-trivial solution for M, the determinant of lambda I minus A has to be equal to the 0 vector. Or sorry, not to the 0 vector. It has to be equal to 0. That should just be a plain old-fashioned 0, and not a vector 0. Which has as its left-hand side a polynomial in lambda and is called the characteristic equation. So the determinant operator for a matrix is something that you guys will learn a lot about in linear algebra, or have learned a lot about, since it's a pre/co-requisite for this class this year. My recommendation is that if you haven't seen the determinant before, I kind of think it's something that they show at lower levels sometimes too, so you may have seen it there. But if you haven't seen the determinant before, learn how to do it for 1 by 1, a 2 by 2, and a 3 by 3, which is pretty just formulaic. You don't have to understand the general procedure, and you'll be good. So it's just a function, it's just a function like any other. You do certain things to the arguments, and you get an output. So the determinant is a function that takes in a matrix and gives you a scalar out. And the scalar is a polynomial in lambda. And we call it the characteristic equation, which is a suggestive term. And we'll come back to that in a second. We define eigenvalues to be the roots of the characteristic equation. Okay? And actually, I already defined eigenvalues, so I realized I probably should have said eigenvalues just are the roots of the characteristic equation. So that is how we solve for them, is to find the roots of this characteristic equation. So you find the determinant of lambda I minus a, you get some polynomial like lambda cubed plus 7 lambda squared plus 3 lambda plus 4 equals 0, and then it's a cubic equation and you solve for the zeros of it. Solve for lambda. 3 solutions, etc. So if A is taken to be the linear state space representation A, so we suggestively just called some matrix A, just some matrix A. It happens to be square, and we also did n by n. We were kind of like foreshadowing the fact that this is what we're going to do to our A matrix in the state space model, our A, B, C, D matrices that describe our system. That A matrix is the A matrix that we're going to consider for this problem. So if A is taken to be the linear state space representation A, and the state space model is converted to an input-output differential equation, right, by procedures that we've discussed a little bit, the resulting ODE's characteristic equation would be identical to this matrix characteristic equation. So we called the ODE's characteristic equation the characteristic equation. And now we're calling this the characteristic equation. And you might think, God, it's two different things. Why are we calling two different things the same name? They're actually equal to each other. So if you were to transform this state space representation with an A matrix A, and you transform that into a transfer function, and you got out a differential equation representation, input-output differential equation representation, the characteristic equation of that you use to find your homogeneous solution, right? When you're solving an input-output ODE, that's the same characteristic equation. So there's like two ways to go to get to this characteristic equation. We don't need to go to an input-output differential equation form to get it anymore. Now we can just find the determinant of lambda I minus a, and we get those lambdas, which are the roots of the characteristic equation. Now, the implication of that is that everything we have already understood about the roots of the characteristic equation of an input-output ODE holds for a system's A matrix eigenvalues. So remember that the input-output ODE's characteristic roots, right, the lambdas that we saw, we also would call them lambdas, right, conveniently. They ended up being very dominant in the response of the system. They're the homogeneous response. This is e to the lambda t, right? E to the each lambda t summed up with different scalings. that's the homogeneous response, and then they play a role in the particular solution as well. So those roots really define a lot about the system. We also learned about how those roots of the characteristic equation dominate stability of a system, right? So what it looks like when it responds, is it first order, second order? Are those roots complex? Are they real? Etc. All has an effect on the response of the system. Turns out that all you need to know are the A matrix eigenvalues, and you get that same information. Okay, pretty cool. It's a big time shortcut if you've modeled your system in state space. Here we consider only the case of n distinct eigenvalues. Okay. For eigenvalues of what we call algebraic multiplicity greater than 1, what we've called repeated roots, see the discussion of lecture B1, which is, I've added an appendix that has a little more advanced topics, which deals with the case of repeated eigenvalues. We're not going to, I'm not going to hold you guys responsible for that. So I'm not going to lecture on that material. It's a little bit more of an advanced topic, more of a maybe grad level topic. It turns out that for that sort of rare case of repeated roots, there's like a whole lot of work you have to do to deal with it. So we're just going to exclude it from our consideration. When we need to worry about eigenvalues and eigenvectors, we won't have any repeated roots. So there's a whole topic of discussion. I thought about last night. I had this moment where I was like, should I? And I was like, appendix. I want to go to yoga today. Okay, so also you guys would not have liked it. So solving for eigenvectors. So we learned how to solve for eigenvalues. Determinant of lambda I minus a. Solve for lambda, and you're good. Solving for eigenvectors. Each eigenvalue, lambda I, has a corresponding eigenvector. Substituting each lambda I into equation 212, which is this one, the form of the equation that we'll typically use, one can solve for a corresponding eigenvector. It's important to note that an eigenvector is unique within a scaling, okay? So like the vector 1, 1, for like a 2 vector, the vector 1, 1, and the vector 2, 2, and the vector 3, 3 are all equivalent eigenvectors, okay? If you have, as long as it's in the same direction, so we'll draw a little 2 vector, 1, 1. In terms of being an eigenvector, all of these are essentially the same eigenvector. It's just defining a direction. So it doesn't actually matter what the scale is of it, which means that when we solve for it, it won't be a unique value. We're going to have a system that has multiple solutions to it. Yeah?
Why would plugging that into 2.12 give you the answer? Because wouldn't that just give you a 0 in parentheses?
No, you solve for n.
So you solve for m in this. So we're going to do an example, but when we plug in a lambda here, lambda I minus a won't be 0. And so we're gonna have to choose an m that makes this equality true, that makes the left-hand side 0. And so and you'll see how we do it. Essentially you plug it in, and then you have multiple possibilities for your solution, and there are different ways of going about it. Whatever is easiest for you. Sometimes you just pick like the x value, like the one of the coordinates essentially, and then the other one's determined from that. It's up to you how you do it, but I'll show you what the sort of problem is that arises. Yeah.
I is just an identity, right?
That's correct. Yeah. So this is the identity matrix, and identity matrix. And so the identity matrix, always, whatever it multiplies, it returns the same thing. So it's like the matrix version of 1, right? If you multiply by 1, you get the same thing back. But we use it to give ourselves a matrix here that is of the same dimension as A. So say A was a 3 by 3 matrix. Then it would be lambda times I as a 3 by 3 matrix, which is 1, 0, 0, 0, 1, 0, 0, 0, 1. Which is to say, 1's along the diagonal and 0's everywhere else. Okay? And a scalar lambda multiplying a matrix gives, so we're just looking at this term right here. I'll say scaled identity matrix by lambda. And so we're going to get its element-wise multiplication here. So lambda times 1 is lambda. Lambda times 0 is 0. So we get lambdas along the diagonal and zeros elsewhere. So that's what that matrix looks like. For a 3 by 3A, it would look like that. For a 4 by 4, there would be another row and another column. Yeah. So let's do an example, which I feel like this is a little abstract, and usually people feel a lot more comfortable with it once they see it in action. So I also wanted to know, this is a footnote here, that lambda I and mi, so the eigenvalues and the eigenvectors, can be complex. And that makes us immediately uncomfortable sometimes. We don't like that. We don't like complex things by nature. But we learn to love them. They do lots of nice things for us. We know that the lambdas can be complex because remember when we found the roots of our characteristic equations, a lot of the most interesting stuff happened when lambda was complex. So, yeah, something to look forward to. We're going to start out with a real example, though. Make you guys feel a little bit more comfortable first. So, let A be this 2 by 2 matrix. So remember, I'm going to just expect you guys to be able to do 2 by 2, 3 by 3, and well, 1 by 1, technically, which sometimes throws people off more than anything. They're like all ready to go for the 3 by 3, and they walk into the test and it's a 1 by 1, and they're like, I don't know what to do. So don't ignore the 1 by 1 possibility. It's not bad. Okay, so we'll do a 2 by 2, and it turns out this one has real eigenvalues and real eigenvectors, but we'll also do some homework where you've got complex values too. It's not fundamentally different. It just requires that the actual manipulations be complex, which is a little more annoying. But let's just sort of walk through this. Let's sort of take it in sort of a methodical way. So the first thing to do is always to solve for the eigenvalues. Okay, that's always the first step. So eigenvalues. So we use let's remember which equation it is. So let's use equation 213, right? So this is the determinant of lambda I minus a is what we're looking for. And actually, before we dive in, let's notice that this term lambda I minus a shows up in all of these, or in both of these expressions, right? Lambda I minus a, lambda I minus a. So actually, lambda I minus a is going to be useful to us not just in this formula. So maybe let's just compute lambda I minus a over here on the side, and then we'll use it in both formulas. Okay. So I guess I'll say first lambda I minus a. Let's compute it. So lambda, the A matrix is a 2 by 2. So what size should I be? Should be a 2 by 2. So 1, 0, 0, 1 is the identity matrix for a 2 by 2. minus a, which is good old 2, -4, -1, -1. And this is, we have to remember how to do matrix addition and subtraction, right? So also, I showed you just a minute ago how to do matrix multiplication by a scalar, which is the lambda just goes in to each of these values, right? So we need to do element-wise subtraction. When you're multiplying matrices, you have to do matrix multiplication, which is not just element-wise multiplication, but when you do subtraction or addition, it's just element-wise. So this first element here is lambda, right? Once you distribute the lambda in there. Lambda minus 2 is the first element. Everybody see that? Okay. What is this element here, the 1, 2 element? Yeah, so it's 0 minus -4, so it's +4. You guys are ready with that answer. You guys are ready to go this Monday morning. I like it. You guys doing this kind of thing? Nice.
Adding the multiplying matrices.
Sweet.
Although, why do you not do a minus lambda?
Still works. Turns out to be the same.
I know. I just asked why.
Oh, I do. I don't know. This is the one that I learned.
Because I did it a minus lambda I, so it does come out to be -4.
Yeah, it works
it's
out.
the same.
The determinant works out to be the same, so it's fine. Yeah. Okay, then we have 0 minus -1. It's +1.
Because I'm against the man.
And then lambda minus -1, lambda +1. I cannot tell you how many times people forget how to add and subtract at this step. I do it too. Like, I don't know what it is. This step, like, it makes me forget, like, this minus sign, almost always forget it's there. Like, the first time. And then, like, I'm actually not good at anything. I'm really good at just, like, checking my errors and debugging. That's really it. I just, like, close that loop faster and faster. Makes it look like I'm better at things. Okay, so this is our lambda I minus a. So we're going to use this again. So now use equation 2.13? Yeah, this one. 2.13. 2.13. We need to know what the determinant is of the matrix lambda minus 2, 4, 1, lambda plus 1. I feel like we might be in like a horror movie. I don't know. It's crazy.
The fourth floor is haunted.
Is it?
Oh, sweet. Yeah.
Is that like a thing?
No, it actually is. There's an actual ghost story with the fourth floor. There was one of the monks who was 19 years old when he died. Fell off the balcony while washing the window or something on the side. I don't remember. And died. And so now supposedly he was like just on the fourth floor at night. You don't see up there and the white clothes and stuff like that.
That's pretty morbid. Really? I don't know. At least we're on the 3rd floor, so we're good, right? We're good on the 3rd floor. Okay, so let's compute this. I know linear algebra really hypes you guys up, but so for a 2x2, it's really easy to do the determinant, and I really don't mind if you guys feel like you like don't really want to learn determinants in general. Learn the 1x1, 2x2, 3x3 cases. So this is the 2x2 one is literally just this element times this element minus this element times this element.
Yeah, it is.
So not too bad. You guys got that. Lambda minus 2 times lambda plus 1. And then minus 4 times 1. Okay. Which gives us lambda squared minus 2 lambda
Minus lambda. Plus lambda.
plus lambda.
Plus lambda.
And then minus 2 minus 4, right? So lambda squared minus lambda minus 6. That's what I did in my notes, so that's a good sign. Okay. And the determinant we want to set equal to 0, right? So we want 0 equals lambda squared minus lambda minus 6, which gives us, using the good old-fashioned quadratic equation,
Or factoring.
or factoring,
Dr. Bennett just rolled over
but
her chair.
yeah, or factoring. Yeah, this one's actually not too bad. What does it factor to?
Factors the quantity lambda minus 3 times lambda plus 2.
That's right. Which gives us
3 or negative 2.
And negative 2, not or.
So what I will typically write is lambda 1 comma 2, which means lambda 1 and lambda 2 are equal to 3 negative 2. And we set an order there, and it's important to recognize the order. So lambda 1 is 3, and lambda 2 is negative 2. So we defined that order. We should stick with that. Okay? All right. So those are our eigenvalues. Now we need to find the eigenvectors. So eigenvalues, that's pretty easy, right? So it must be the eigenvectors that are the hard part. so eigenvectors. I said let's use 212, right? This equation. So 212. It says 212, and then let's plug in each lambda separately. So we'll do first lambda 1 equals 3. So for lambda 1 equals 3, maybe it's at an angle. There we go. For lambda 1 equals 3, we have the following expression from 212. So we have lambda I minus a, which remember is just this thing. We're just going to plug in that lambda 1 equals 3. So we've got 3 minus 2, 4, 1, 3 plus 1. Okay, so that was the lambda I minus a part. And then the equation says times m, which is hopefully going to be our eigenvector if we can find it. And we could just write m here, but I think it is helpful to actually expand that out. And I'm going to call this, so we're working with m1, right? So m1 and then the first element, and then m1 and then the second element, okay? So we're going to just go ahead and write out the two unknown elements of the vector, of the eigenvector. That has to be equal to, according to equation 212, the 0 vector, right? Which is 0 and 0. So this defines a linear system. But actually, there are going to be multiple solutions to this linear system because we plugged in an eigenvalue. It always happens. So let's go ahead and rewrite this. Let's go ahead and compute what each of these values is in this matrix. So 3 minus 2 is 1, 4, 1, 3 plus 1 is 4. And we see that the two equations defined here are linearly what? Dependent, yeah. They're the same equation, actually. Identical. They don't always end up being identically the same equation, but they might be like 2 and 8 and 1 and 4. But they're the same equation in the sense that they're not independent equations. They're along the same vector. That's how it's defined. So, what do? Pick a value. You can pick any value for one of them and solve for the other value. I don't know. It's sort of up to you how you like to feel about this. So some people are like, okay, I'm going to pick M1 to just be 1 every time. I'll pick the first one to be 1, and then the other one gets determined from that. It's up to you. I don't care. So this tells us that M1 is equal to, remember, this can be scaled. So technically, we should, I don't know, say like any scaling factor. So you might say like alpha, like any scaling factor. All right. Any scaling of the following vector. And we can write anything in there, right, as long as it satisfies this. So say we chose M11 to be 1. Okay? This top equation would read M11 plus 4 times M12 equals 0. So a little scratch on the side here. 1 times, if we said M11 had to be 1, plus 4 times M12 has to equal 0. This you can solve, right? So M12 is equal to negative 1/4. So that works. You could have also chosen, something that people will do, actually what I like to do, let's just say, is I like to say, oh, well, this is a 1. I would multiply that by negative 4. So M11 is negative 4, and then M12 is 1, and then negative 4 plus 4 is 0. It doesn't matter. It's the same. It's totally valid within a scaling factor. Okay, so we found an eigenvector. So far, nothing's hard. It must be the next eigenvector that's hard. Okay, let's figure this out. Okay, so lambda 2 equals negative 2. And we once again use good old lambda I minus a equation or expression that we came up with back here. So we have negative 2 minus 2, 4, 1, negative 2 plus 1. And then this is M2, right? So M21, M22 equals 0, 0. So let's go ahead and once again rewrite this. So negative 4, 4, 1, negative 1. There is a lot of writing. That's the hardest part, I think, the writing part. M2 is equal to, once again, any scaling factor. So we'll just put in another scaling factor, beta. But often we'll just ignore that.
But it does have to be different, right?
Yeah, it doesn't, well, I mean, you could choose them to be the same, but in general, they could be different. So it's good to choose a different scaling factor. This is just there to remind us. A lot of times people will just say m1 equals 1 and then negative 1/4. And then it's just known that it also equals any scaling of that. Okay, m2 is beta times some. So we have to choose an m2 and m1. If you chose m2 1 to be 1, like we did before, then we would have negative 4 times 1 plus 4 times something has to equal 0. What do you guys think? It worked. So when I say, so I do want to clarify something, because once again, we got here and it was easy too. When I say things about how it's easy and whatever, what I mean is you don't need to be intimidated by it. A lot of people get intimidated by it, and once you understand it, it's easy. What I don't mean to do is to belittle anyone who's having a hard time understanding it, because I also have a hard time understanding things all the time. So I realized as I was talking that maybe that sounded a little bit belittling people who are struggling with it. It's really my attempt to reduce anxiety about doing these problems, because they're actually not too bad, I don't think. I think you guys can do all the steps required to make this happen. So this was the 2x2. The most complicated you guys will have to do by hand is up to a 3x3. The determinant is a little bit more complicated, but not too bad. The other nuance that I might throw at you by hand, which would be a homework problem and potentially could show up on an exam, is a complex one. So if your lambdas are complex, so your roots of your characteristic equation here, you could factor still, or you could use quadratic formula to discover that the roots are in fact complex. Okay. So that part doesn't change at all, right? So we would still go through this and we would find, oh, the roots are complex. So you still have the eigenvalues, nothing's changed, right? You plug in your eigenvalues into your lambda I minus a, and you're going to have potentially complex m1 and m2 required in order to make that left-hand side 0, okay? Which is, you guys know how to do multiplying complex numbers together, adding them together. You guys know how to do all that. So there's nothing fundamentally different about it than what we just did. But I do think it can kind of look a little scarier. You got to write more. Once again, that's the worst part. You got to write more stuff. But yeah, so there's nothing fundamentally intimidating here. But so if you guys just understand how to do it up to one more order of matrix higher and then including complex, you've got everything you need to do an exam.
It's literally 1 minus lambda.
And 1 by 1.
Yeah, 1 by 1. Don't forget about 1 by 1.
Lambda I is just lambda, and so we have a minus lambda. It's just whatever your number is minus lambda.
Yeah.
The determinant of
The determinant of a 1 by 1. There's a good exercise for the class. Look up how to do the determinant of a 1 by 1 matrix.
also for
Okay.
3 by 3s.
And a 3 by 3.
I don't know the whole picking a number, but you should probably row reduce 3 by 3 and find 3 variables.
So there's a suggestion to do that. You may find that to be helpful. You can employ all these techniques that you've learned throughout your classes. I don't think that they're usually super necessary, but they can be helpful. So I will say we're going to start using this in the next lecture on Wednesday, and we'll do some really cool stuff with it. One of the things that I assume is that we'll be doing more complicated problems above 3 by 3 using MATLAB or Python or something, which has functions to do all these things, which is really nice. So yeah, In MATLAB, I'm going to give away the secret. Those of you who want to check your work, Eig
Hey,
is the function you're looking for. It finds not just the eigenvalues, but also the eigenvectors.
yeah.
So it's a good way to check.
Another really neat way to check is just make sure you have the same equation on top and on bottom.
Yeah, you should be able to turn one into the other by scaling it. Yeah. All right. Thanks, guys.